Okay, hello everyone. The next concept that we will see is this information and sigma fields or sigma algebras. Again, you can draw parallel to what we have done in discrete time model. We will continue with the continuous time version of what we have done. Okay. For understanding, you can always go back and draw a parallel with discrete. That's okay. As you see, this no arbitrage pricing theory, which is used to price the derivative securities, is based on contingency plan, right. So, to price the derivative security, what we do is we try to find the initial wealth that is needed to set up a hedge for the short position, right. So, which means that to completely replicate the things, right. Now, the hedge must specify what positions we will take, and that requires the information from the present time till the future point of time, till the maturity, so to say, right. And this to make the contingency plan, we need a way to mathematically model the information in which our future decisions will be based, right. And in binomial, this we made an analogy to the coin toss, and then each time period we said that okay, it is as if the one more coin toss is getting added and how things are, information is gathered, and that is the way we modeled it for the discrete time. In continuous time also it is along similar line, but we need a little bit more sophisticated model way to model the information, and that is based on basically. So, it is based on in continuous times sets resolved by the information, right. So, this is same in discrete, but it is little bit complex here, that is all. Okay. So, now what is the filtration, right. So, this filtration would consist of sets resolved by the information available up to time t, right. So, the definition is as follows: you have a omega be non-empty set and let t be a fixed positive number and assume that for each t in this interval 0 to t, there is a sigma field or a sigma algebra which we call f of t. Assume further that if you pick 2 time points s and t such that s less than or equal to c, then every set in Fs is also in Ft. Okay. Then we call the collection which is Ft a filtration, right. Just like in discrete time, what we have here, an increasing collection of, rather than now sequence, it is a collection of sigma fields, it is a family, because t is belongs to 0 to t in a continuum manner. So, what we have is a collection of increasing sigma fields is what then we call it a filtration, which is much like the similar. Okay. So, this collection or this filtration tells us the information we will have at all with the future times. More precisely, if suppose at t, right, we will know we will know for each set in f of t, if you pick, we will know whether the true omega lies in that set or not. That is what would be. So, this for if the information or the sets resolved by the information at time t means what? We will know for each set you pick, and you pick a true omega, we will be able to say whether for each set whether this omega belongs to this or it does not belong to for with certainty, right. So, that is what the sets will be of the nature of the sets in this sigma field F. Okay. Now, before we go further, let us simplify the notation. Okay. So, simplify the notation. So, from here on, what we will do, instead of saying this as a function of t, so what we will do is we will just make this as a subscript, so that for readability it is just easier way of denoting, but the meaning is it is a function of t. Okay. Similarly, suppose if you have a process, right, something x, a random variable later we are going to see. So, this we will be denoting it in this manner. So, x t, right, this f t, s x t, anything is a function of t. If there is only one, then obviously we will put it in this. Suppose if it is more than one, then of course we may expand it with 2. So, this is for the notation, right. So, this is you just keep that in mind. From now onwards, when we write f sub t in the subscript t, which means f of t is a function of t. I mean, we are looking at as a function of t. Okay. So, just for simplicity we will write it, which is common in stochastic process area. So, it is nothing unusual that we are doing it. Okay. Now, let us look at an example. Okay. Let us take this collection of what we call the set of all continuous functions on 0 to t taking value 0 at 0. Okay. So, this is what it is. So, suppose if there is a function f which is a continuous function on 0 1 defined on 0 1 at 0 to t, and f of 0 is 0, that is what. So, any such f is what then this collection is. Okay. Now, at t, if you look at certain sets, subsets are resolved by time t, which means a typical omega here we mean is a continuous function, a function in this omega, right. And whatever the sets are resolved, okay, so we put that into f t and we make a sigma field, and whatever, if you simply put whatever sets that are all resolved by a time t, then that will be a sigma field. Okay. So, let us not get into the details, but that is you can take it. Okay. Now, which means that all the sets that can be described by the path up to time t of those continuous functions, they all will be resolved by this thing. Okay. So, certain sets are resolved and some are not. Okay. Say for example, if you take set of all omega such that, so if I look at something like this, say max or min or sum or at any particular point of time, but the time is omega of s is say less than or equal to 5. Suppose if I look at here, for some omega which is a continuous function here. So, we denote it in the usual way omega. So, this is resolved, whereas if I look at a set of this form, right, set of all omega such that my omega at time t is say greater than 5. So, this is not, okay. So, this is not, this is yes, this is resolved. So, this is the kind of sets that we are putting inside this FT to form this. So, this is basically you can see this is a path of this function or the function values observed between 0 to t. If anything, it can be described by the set, right. So, then this will all be in this form, like these are all the sets that are resolved by the thing, okay. So, this example provides the simplest setting in which we may construct later on the Brownian motion. If we could assign probabilities to each of these sets in FT, as we said, you know, when we talk about probability being assigned in a continuous time model, it is actually sets in the sigma field rather than the atoms. And this, if we assign only the probabilities, then of course all these things will become the paths of the Brownian motion that we are going to define a little later, okay. Recall atom concept here we are not saying, because rather we are directly dealing with the sets in the sigma field, typically as happens in a continuous time or infinite probability spaces, and we work with all the sets in FT directly rather than the atoms. And atoms if you typically take, and especially the sets which have positive probability, because atoms are generally have a probability of 0 in such situations, okay. This is one way of describing the information through. Another way to acquire information is through a random variable, okay. So, recall the definition that we have written for a random variable x, the quantity sigma of x. What is this? This is the sigma field generated by the random variable x, or which is nothing but the collection of all subsets of the form x belong to B for B a Borel set. So, you take a Borel set B and you collect all those omegas which gives the value of x in the Borel set P, and you collect all such sets, that will be the sigma phi generated by x. This is what we have seen. This definition which we already know, we have seen it in discrete time. This is exactly same as in the definition. Now, extend these two, again in discrete time also we have extended, but you know there it was little much more convenient because you had a sequence of random variables. Now, you extend this to a family of random variables, right. So, suppose if we have, suppose if we have say x, which is nothing but we denote the collection. So, this is sometimes very boldly we can write x t, t belongs to some t, right. So, this is the set t, or I can make this as for our convenience in a usual way this collection x t, right. Now, we can define the filtration given by this or filtration generated by this family of random variables rather than a sequence of random variables as follows, okay. So, what we denote? We denote this by this f superscript x. Whenever we write this, we mean that this is a sigma field or a filtration generated by x, which is in our case is nothing but f t of x, right. So, t belonging to 0 to t. Remember, we are now writing f subscript t rather than as a function of t, but it means the same. Where what is my this f t of x is nothing but the sigma field generated by this family up to time t, right. I can write it something like this, where what it means is, so in discrete you recall that we said that this one is sigma of x naught, sigma of x naught comma x1, sigma of x naught comma x1 comma x2 and so on, we have extended. Now again similar thing, but now since you do not have this x naught x1, you have there are infinite number of points in between, so we have writing it in this family. So this is the family, and the sigma field generated by this particular family is what my f t of x. What does that mean? This is the smallest sigma field with respect to which each of these random variable x u for u less than or equal to t is measurable, right. That is what is the other way when you want to say sigma field generated by a random variable or random variables, right. So this is what we would mean. So later on we will be considering mainly the filtration generated by some family of random variables. Okay. So that is nothing but the stochastic process, right. So this is some collection of random variables or some random process or stochastic process, which is what this f x. This is the most common filtration that we will be using it later on. Okay. Right. So this is the filtration, basically what we will do, right. Now connected with this, right, we also recall the definition of measurability. Okay. Now when do we suppose you have a x which is a random variable on omega f, recall that you do not need the probability to define x, let G be a sigma field over omega, which means sigma field of subsets of omega, if every set in this is also in G, then we say that x is G measurable. Okay. What is mean? The measurability, measurable, right, that means that if and only if the information is G is sufficient to determine the precise value of the random variable x. That is what measurability would mean in practice, right. And sigma x's are what? Sigma x is sigma of x, the sigma field generated by the random variable x is nothing but the information content of the random variable. It has exactly same information as you have observing you have by observing the random variable x. So it is means that if each of these sets is there in G, means that G also has at least that much information, then we say x is G measurable. So if you know G, then you know x precisely. That means what is the value of the random variable? There is no more randomness essentially in the case. Okay. Now if x is G measurable, then you can also see x is G measurable, then you can see that f of some function of x is also G measurable, where the function we again recall that this is a Borel measurable function, right. So all smooth enough function that we are going to consider in this case. Okay. Now this gives also rise to another definition next, which is you pick a collection. Now as you see, a collection be a collection or a family of random variables, that means that what, which is a stochastic process, right. So, what do you mean by stochastic process? I mean, we have seen discrete time, but again you may recall, even if not, there is nothing big about it. So, we have a family of collection indexed by a parameter t here, right. So, this is just a family. So, this family is what is generally referred to as stochastic process, and depending upon the nature of the relationship between the random variables in this collection. So, we give a name to such a stochastic process. We have already seen Martingale's Markov process, right. So, which are all depending upon what is the nature of the relationship between the random variables, that is what you have. Okay. Now, we pick, let omega be a non-empty, the usual assumptions, non-empty set, which is essentially the sample space here with filtration, say f t, where t belongs to, even if you do not write, we always assume that this is. Then the stochastic process x, which means this collection is an adapted stochastic process or random process if x t is f t measurable for each t, right. So, what do we mean? Because from now on we may say that some process is an adapted process. Adapted process means that in the process, if I take the tth element of the process, then that tth element is corresponding to the filtration, the f measurable with respect to the tth element in the filtration, which is f t, which is what we call a process of that nature is adapted process, right. So, in discrete time also we have seen the wealth process, the portfolio process, the asset price process, right. All of them were adapted, means that once you reach up to that point of time, then you know the value exactly of that. Prior to that you will not know, right. So, that is what it is. So, this is what it discloses. So, again in continuous time model also you have the asset price process, portfolio process, wealth process, all of them would be adapted processes, right. So, this is the definition of an adapted process when we use this here. So, the next concept that we will look into, that is independence. Okay. So, you have a random variable, you have a sigma field. Now, on the one extreme, if this random variable is measurable with respect to the sigma field that is given. Now, the other extreme is that the random variable is independent of the sigma field given, right. Now, what we saw in the case of measurability, we saw that the information in G will determine completely the random variable x. But in the case of independence, the information in G is of no value to determine the value of x. The intermediate case is what we will take it a bit later, is what is conditional expectation case, right. So, let us first look at the other extreme, which is independence, and since you already know from the earlier theory that independence is connected with probability measure. So, by changing the probability measure, the independence nature of the either between the random variables or between the two sets or anything might be broken, right. So, you need to keep that in mind. Okay. Now, let us define what we may have. So, as usual we have a probability space, okay, and let us take two sub sigma fields of f, okay. Say let G and H be sub sigma fields of f Okay. Then we say these two sigma fields, okay, G and H are independent if okay. It is much similar to independence of two events, but now when we talk about independence of two sigma fields, we mean the a set from one sigma field and an arbitrary set from the other sigma field, right. These two should be independent for all such arbitrary sets, right. That is what the sigma fields mean. So, extending this, you can also talk about, you know, two random variables, say x and y are independent if sigma x and sigma y are independent, right. Sigma x, sigma field are sigma fields, right. So, this is what we mean when we say two random variables are independent. Similarly, a random variable of x is independent of a sigma field G if sigma x and G are independent. So, there is nothing to this case. Now, you can also extend the definition to a general n, right. So, you cannot talk about n random variables being independent of each other and n sigma fields and so on, extending same thing that you have extended. Okay. Now, but more importantly, we say a sequence of random variables, say x n, is independent if for every positive integer n, the n random variables, say from this collection which is x 1, x 2, x n, they are independent. So, if this is true, if for a collection of random variables, if this is true for each finite set when you pick, right. So, this claim above that we use here, that we are talking about independence of random variable in terms of the underlying sigma field generated by the random variables, is much more strong. I mean, not necessarily strong in the sense of anything extra that it gives, but it is easier if you to view it through this way, then it will be useful to prove many things. Say for example, useful, this way of thing is useful if you want to prove, say for example, to prove f x and g of y are independent when x and y are independent. Okay. So, if we talk in terms of the sigma fields, the proof of this is simple straight line, simple not straight line, it is straight away, it follows from there, but otherwise, but it is difficult to check in practice. So, that is where your usual definition of independent, which you might be aware, would come into play, which requires the knowledge of what we call joint probability distributions, right. So, this is, you might have idea about this probability, but let us take the simple case 2, but that is exactly similar in the case of more than 2. Okay. So, let x, y be random variables, right, the pair. Okay. So, the pair, so which means if I look at this, so this takes values in R2, right. So, if I consider this as a pair, so this is a random vector, which is what we generally call, or a two dimensional random variable, which means that each of those one dimensional random variables that we have. Now, the joint probability distribution is given by, which we call P x y of some set C as defined by this pair taking values in the set C for all C in this collection. What is this collection? This is the collection of Borel sets over R2, right. So, but we have not seen this yet so far, but it is much similar to the Borel sigma field over R. In R, what did we do? We took closed intervals, right. We took closed intervals of the form A B, and we generated a sigma field, that is what Borel sigma field over R. So, in this case, in R2 you can take rectangles in R2 and you generate a sigma field over R2 with generating class as being the rectangles in R2. So, that is what you will end up with, the Borel sigma field over R2. So, this is a much like say for example, you can take sets of the form this, right, which is nothing but the rectangle. So, and this is basically the Cartesian product that we are talking about. So, this will represent some rectangle in R2. So, now you take this as the generating class and you generate the sigma fields, sigma field over such rectangle. So, then what you get is the Borel sigma field. So, this is just that thing that you have extending the idea of here. Now, you also know the joint CDF or the cumulative distribution function of this two dimensional random variable sum A B as probability of this pair belonging to minus infinity comma A, this set product, Cartesian product with this collection, right. So, this is nothing but probability of x less than A, y less than B for all A B in R is what is the equivalent way in which you can also represent as the joint CDF. Now, we also say that a non-negative function, say f x y, if you want subscript you can also put x y, is a joint PDF for x y if you can write this as A B right. So, this is the joint case, and similarly you could also have the marginals. So, these are all ideas that we are just recalling. So, P x of A is nothing but from A cross R for all A in Borel set of R. Similarly, P y of B is P x y of R cross B for all Borel set over R, right. So, equivalently you can also define f x of A as probability P x of minus infinity A and f y of B as P y of minus infinity B, right. And similarly, this is marginal distributions and marginal PDFs. Also, you would have f, if you can write A f x of x dx for all A in R, and f y of say B is equal to minus infinity to B f y of y dy for all, sorry, for all. So, these are marginal distribution. Okay. Now, given these definitions, now we have the result which tells us how to check for independence in practice. Okay. So, let us pick two random variables. Let x and y be random variables. Then the following, whatever we are going to write, are equivalent. Okay. What are they? We say that x and y are independent. B, the joint probability distribution, if it factors as here for all sets A, B, which are Borel sets. C, the joint CDF factors, right, the joint CDF factors. D, which is basically what we call the joint moment generating function factors into product of into product. Okay. So, what does that mean? So, this MGF you might be aware, or even if not, let us write in the original form itself. So, this is e to the power some u times x plus some v times y. This particular expectation is expectation of e to the power u x into expectation of v y for all u v in R, for which the expectation is finite. As you know, MGF may not exist for a particular random variable. So, we need to worry about the existence. So, for which whenever this exists, so this is true, that the MGF factors into its product of MGF of the marginals. Now, E, the joint PDF, again the density may not exist, but whenever it exists. Okay. So, the joint PDF factors into product for all x, y in R. Okay. As a corollary to this, we will also see the independence implies that expectation of x, y, the product is expectation of into expectation of y, provided of course this is integrable or finite. Okay. Now this, now you recall the definitions of what we call variance of x, which is nothing but expectation of x minus expectation of x the whole square, and you have covariance of x y, which is expectation of x minus expectation of x and y minus expectation of y, right. This is what is the covariance, and also the correlation coefficient of x y, which is covariance of x y divided by variance of x into variance of y, the square root of it, right. This is what the correlation coefficients, and we know minus 1 less than or equal to rho x y less than or equal to 1 is the range. Now this is whenever covariance of x y equal to 0, that is what we call it as uncorrelated. Okay. So in general, so what this the corollary which we wrote just before means is that the independence implies uncorrelation, but uncorrelation need not imply independence. Of course, you can find examples easily. So this is one way implication, but as far as the independence checking is concerned, you can talk either in terms of the PDF, in terms of MGF, in terms of distribution function CDF, or in terms of the distribution its measure itself. Any one of them you can use to check for independence of two random variables x and y. Right. For checking this, this is what we would be using it. Okay. Now, so we will also need the idea of multivariate normal. We know the univariate normal distribution. Okay. So the random, we will also need this idea as we go forward. So let us take the random variable x, x1, x2, say xn is what we call jointly normal, or this has a joint normal distribution if it has the joint PDF, which we write the in terms of this vector as 1 over 2 pi to the power n, and determinant of this matrix C, this under root, and e to the power minus half x bar minus mu bar into C inverse into x bar minus mu bar its transpose. Okay. For x in Rn, right, where what are these? My mu is mu 1, mu 2 and so on, mu n is the vector of expectations or the means of these random variables individually, and this matrix C is the positive definite matrix of covariance. We are assuming that this matrix is positive definite matrix of covariances is what then you have. Okay. Now, if you look at this multivariate normal, and if you look at when this multivariate normal will be or this n random variables are independent, you can easily observe that the density, if I look at here, so in this case the density factors into product into the product of n normal densities if and only if C is a diagonal matrix. Okay. We have assumed positive definite just to ensure that its inverse exists and the random variables are jointly normal. Now, in this particular case, if this C is a diagonal matrix, then you would see that this the quantity that we have written within exponent, right. So, will be, so the determinant and the quantity that we have written into the exponent, they all will be factoring. You can write it as simply as sum of the individual element without anything. So, you will be able to see that then the this factors into the product of marginal densities of the normal PDFs that you have here. Okay. Now, as a special case, so for n is equal to 2 case if you look at it, so this factorization or this into the products happens. So, this is x and y in for n is equal to 2 case, x and y are independent if and only if my rho is 0 or simply rho x y or rho is 0. Okay. So, this is a special case with respect to the normal, that in normal case that this uncorrelation and independence are equal, simple. So, this is additional advantage. In general this is not true, but in case of joint in normal distribution this is true, right. So, this is uncorrelation and independence imply each other in case of joint normal case. Okay. Now, for n is equal to 2 case, you can also see this easily. If you look at for simplicity, I am also writing down the density sigma 1, sigma 2 and this is 1 minus rho square e to the power minus 1 by twice 1 minus rho square. Now, x minus mu 1 whole square by sigma 1 square and 2 rho x minus mu 1 into x minus mu 2 by sigma 1 sigma 2 plus y minus mu 2 square by sigma 2 square. Now, you can easily see if I put rho is equal to 0, this quantity becomes 0 and this is you can see easily it factors into the two quantities here. So, this becomes 0, this becomes 0. So, this becomes product of two standard normal densities, this factors into. That is what we mean when we say this one. Okay. So, in case of normal, we also know if I take linear combinations, okay, linear combinations of jointly normal random variables are jointly normal. Okay. And since independent normal is jointly normal, okay, so in order to get a generic or a much more general multivariate normal, one way is you take independent normals and take linear combinations of those independent normals to arrive at the required multivariate normal. Okay. On the other hand, if you have a multivariate normal distribution, then it can be written as a linear combination of independent normal random variable, right. So, that is what will be helpful as we go along, because whenever you have dependent normals, but they are jointly normal, but they are not independent, then you can write it down in terms of as a linear combination of linear normal random variables. And while dealing with another advantage with the normal distribution is that since the normal distribution is characterized by its mean and variance, and the covariances in general in case of multivariate normal means and covariances, then it is enough if you work with the means and covariance terms. You need not, it is equivalent to working with the case of the densities, right. So, dealing with means is sufficient. So, now let us consider an example. This example we will keep repeating. So, let us call this as an example A, example A. Now, what we have? So, let x y be jointly normal with PDF as above, right. Since it is a two dimensional case, so what we mean is this is the bivariate normal distribution we call it, and this is the density of the bivariate normal, right. So, this is called bivariate normal, general bivariate normal density, the bivariate normal distribution. Now, define a random variable W as this sigma 1 times x, then the claim is x and W are independent. Okay. You can see by looking at the covariance of x and W, right. So, which you can easily see is covariance of x and y minus rho times this of covariance of x comma x, which is equal to 0, right. So, covariance of x and W is 0 and hence x and W are independent, right. And what does its mean? Let us that is done. So, this is proof is only this much is done. Now, for further reference, we also need the mean and variance of this W, this particular random variable W. So, let us call this as mu 3, which is expectation of W, which is in this particular case would be mu 2 minus rho sigma 2 over sigma 1 times mu 1, and sigma 3 square, which is nothing but the variance of W. You can see that this will be, you can just substitute the quantities and do this little algebraic manipulation to see that this variance of this W is nothing but this part. Okay. So, this we will require when we go as we go ahead. So, we will just keep that in a moment. Okay. Now, this is the other extreme, independence, and how do we check, and in case of multivariate normal, like how this is related in this case. Now, we will go to our general case of a relationship between random variable and sigma field, where x is neither measurable with respect to G nor independent of G. Then what we have? We have to really now estimate. We cannot determine the precise value of x, right. In that case, what we have to do is that we have some information which is useful to know about x. So, which means that we will use this information to estimate x, which is what is the more common case. So, we cannot precisely calculate x, but we can estimate x, and that estimate is what we call condition expectation. In discrete time also, we said in what sense we said this is the best estimate, which is the mean square error sense, right. So, that is true here also, and we also arrived at a definition. In discrete we defined it slightly differently, and we arrived at a characterization which is equivalent, and we said that the characterization is going to be the definition which we are going to take in the continuous time model, and that is precisely we will state it now. So, what we have? So, we have a probability space be a probability space, okay, and let G be a sub sigma field of F, and let x be a random variable that is either non-negative or integrable, though we state this thing for both the cases, we will mostly assume that this is integrable case. So, this is, but this is true for even non-negative. Okay. Then the conditional expectation of x given g denoted by x given g, which okay, we will keep it as it is. You may call it as some y if it is that is convenient, is any random variable that satisfies a two condition. Expectation of x given g is g measurable. This is called the measurability property. P, expectation of indicator function of this quantity must be equal to expectation of I a for all a in g, which is, if you write in terms of your Lebesgue integral, it would mean this. This is called partial averaging property, right. So, this is the partial. You recall in discrete time also we said these two properties only defines the conditional distribution. Now, note if our G is simply a sigma field generated by some random variable, say W, then we write this as expectation of x given W instead of expectation of x given sigma W, right. But what we mean is this one only, but we simply write this in this form. Now, as far as the existence of this such a quantity is concerned, yes, as long as your expectation of x is, since we assumed integrable, so expectation of x is finite, such a conditional expectation exists and unique almost surely, right. So, that proof of course, we will not need it. Quickly recall the properties that we have seen in discrete time, which is also hold good true in continuous time. The first is the linearity property, then taking out what is known property, which means x is g measurable, then you can take it out from the estimation. The third is basically the tower property or the iterated conditioning property, which essentially means expectation of x given g is expectation of x given h, which is also would be same as expectation of x given h for two subsigma fields. H is a subsigma field of G. Now, D, expectation of x given g is expectation of x for x is for all random variables x for which is independent of g, and E expectation of phi of x given g is greater than or equal to phi of expectation of x given g for phi convex, and this is what is known as the Jensen's inequality as we have seen. Now, we also see the expectation of x given g as simply expectation of x, which means this estimate expectation x given g is an unbiased estimate for the quantity that we have, that is expectation of x. Now, let us continue or look at the example A that we have considered earlier, and let my g in this particular case would be given by this. Okay. We know that we have y, we can write it as rho sigma 2 by sigma 1 x plus w. Remember, x and y are jointly normal with the correlation coefficient rho. Then y can be written as this constant times x plus w, where x and w are independent, right. Now, you can estimate y based on x, right. Now, we are coming back to the estimate part, because now x and y are not independent, and the y is also not measurable with respect to sigma x. Now, when you want to estimate y using x, right. So, what we have is precisely expectation of y given x, this notation which we already explained, it is y given the sigma phi generated by x is what we are looking at it. So, this is rho sigma 2 by sigma 1 times x plus expectation of w, right. Here we have used two properties or three properties rather, if you have to see, like first you have used linearity property, then x is measurable with respect to x and w is independent with respect to x. All these properties will use, if you use you will end up with this. So, this essentially means this one, and this is what is called the linear regression line or linear regression equation. Okay. And you notice that this quantity is, so expectation of y given x is simply this quantity, right, which is sigma x measurable and satisfies the partial averaging property. You have to take any particular set and then look at whether this satisfies this and see. Okay. So, this is what we have. Now, we also known the lemma in discrete time, which is also we will restate here for convenience, which is called the independence lemma, which helps us to compute or evaluate the condition expectation of x given g in a much easier way. Okay. So, what we have, we just recall that you have omega f p be a probability space and g be a sub sigma field of f. Now, you pick some collection of random variables, say x1, x2 and so on xk or g measurable, and y1, y2 and so on some yl or independent of G. Okay. Now, let f x1 to xk, y1 to yl be a function of k plus l variables, and define this functions g of x1, x2 and so on xk to be expectation of f of x1, x2, xk, comma y1, y2 and so on yl, right. So, you take this function, replace the dummy variables y1 to yl by the corresponding random variables y1 to yl, and take the expectation with respect to that quantity, and that is what you call it as z, right. That is what you call it as g, the function g. Then what is the claim? Expectation of f of say x1, x2, xk, y1, y2, yl given some g, this condition expectation of this function of this k plus l random variables is given by this quantity. Okay. So, now example A, we will continue. Okay, previously also this is example A continued. So, here also now we are continuing this. So, what we want to know? So, we want to estimate what is our objective? Objective is some function of x and y we want to estimate which is based on the random variable x. Now, we cannot use independence lemma directly in this situation, because based on x, of course, x is measurable with respect to x, or rather sigma x, but y is neither independent of x nor measurable with respect to x. But then how do we estimate, right? But we know a way, right, because this y can be expressed as a linear combination of w and x, where w and x have the required property, right. So, we can use that idea to estimate this, right. So, since we know that y can be written as sigma 2 by sigma 1 x plus w, where now if I instead of this f x y, if I replace this y by this quantity, then the random variables involved in the function are x and w, where one of them is measurable with respect to g, the other is independent of g. Then I can use my independence lemma to estimate or to compute this quantity, right. So, now we can apply the independence lemma. So, define g of x to be expectation of f of, keep this x at dummy variable which is measured with respect to this. Now, rho sigma 2 over sigma 1 x plus the random variable w, right. I compute this expectation. Now, what is this expectation? This expectation, as you know, sigma 3 which we have already computed is what, this x rho sigma 2 by sigma 1 x plus w e to the power minus half w minus mu 3 by sigma 3 square dw. So, this is the function g. So, if I evaluate this quantity, then I will get the function g, and I can see that this one f of x comma y given x is then would generally be this g of x. Okay. Now, this, so we now have all the ingredients to define the two processes that we might use. Okay. So, what we have now, you have a probability space and t greater than 0 is a fixed positive number, and you also have a filtration connected with f, right, connected with f, and essentially note. So, basically here you can note separate this f is generally this f at capital T, right. So, this is what we have. Now, consider an adapted process. We already taken adapted process, say MT, again as we said it is a function of T, that is what we have it. Now, A, if expectation of MT given Fs is Ms for all 0 less than or equal to S less than or equal to T less than or equal to capital T, then this process MT is a martingale. B, if this one is greater than or equal to Ms for all, then this is a sub-martingale, and C, this is less than or equal to Ms, so then this is a super martingale. Even from the discrete time notions, you know what is the meaning of martingales, which neither tend to increase nor fall the process, the expected values, the average value, right. Whereas, in the case of submartingale it tends to increase, and if super martingale case it tends to fall. So, this is the same definition that we have seen it in case of discrete, but only thing is now time is continuous. So, this is we have. Now, the another one is again, so you have a this with the same basic assumptions about probability space, time and filtration. Now, consider an adapted process. So, now let us call this as adapted stochastic process, what we mean. So, 0 less than or equal to T less than or equal to T. Now, what we will assume? We will assume that for all 0 less than or equal to S less than or equal to T less than or equal to capital T, and for every non-negative Borel measurable function f, there is another Borel measurable function g such that expectation of f of x t given Fs, the filtration is this, then this process x, which is nothing but this collection, is a Markov process. Okay. So, note that just like in the discrete time case, this f may depend on t as well, right. So, if we write in that case the above this not quantity, then we do not need a g separately, because the t dependency we are bringing it inside that quantity itself. So, you can write this the above as f of t x t given f s, because now the t dependency comes in. So, you can write this in this form. Okay. Then f satisfies a partial differential equation. If this is true, then we can write the above is this, which is the Markov property. Then this f will satisfy a PDE, and we can find f from the PDE by solving it. The Black-Scholes-Merton PDE that we will encounter, we will see later, is a special case of this. Okay. So, remember here what we are dealing with conditional expectation when we are looking at this martingales, Markov process and so on, and the conditional. So, we need to find a g. If we know that this is a Markov process, then a function of Markov process given a filtration is given by another function of the Markov process at that point of time. Now, that satisfies this kind of relationship. If you have, then this satisfies PDE. By solving the PDE, you get the functional form of f, then hence you have obtained the required solution to this expectation. So, we are trying to estimate this, which is again given by in terms of function f. Now, to find, if you find f, you are done, right. So, that is what we will use. Okay. So, this much is what then we have it now for the case of information, conditional expectation and the things. Okay. Next, we will see in the next lecture about the Brownian motion concepts. Bye.